Download this code from codegive.com, link in the description below. Creating a circular buffer in C and C++ for embedded systems. A circular buffer, also known as a ring buffer, is a data structure that uses a single, fixed-size buffer as if it were connected end-to-end. This allows it to be used as a FIFO, first in, first out, queue in a memory-efficient way, without needing to constantly reallocate memory. They are especially useful in embedded systems where memory is limited and performance is critical. They are excellent for handling asynchronous data streams, like sensor data, audio streams, or communication data. This tutorial will cover 1. Concept and benefits of circular buffers *, why use them? What problems do they solve? 2. Core implementation details *, understanding the pointers, how to handle wrapping, and avoiding common pitfalls. 3. C implementation *, a detailed C implementation with clear explanations. 4. C++ implementation *, a more object-oriented C++ implementation using classes. 5. Considerations for embedded systems *, important factors to consider when using circular buffers in embedded environments. 6. Error handling and thread safety *, adding robustness to the implementation. 7. Testing *, how to test your circular buffer implementation. 8. Optimizations *, potential performance improvements. 9. Use cases common applications. 1. Concept and benefits. The core idea behind a circular buffer is to treat a fixed-size array as a continuous loop. 2 pointers, or indices, keep track of the read, head, and write, tail, positions. When either pointer reaches the end of the array, it wraps around to the beginning. Benefits *. Fixed memory usage *. The buffer size is determined at initialization, so there are no dynamic memory allocations, no malloc or new. This is crucial in embedded systems where memory fragmentation can be a problem. *. Efficient data storage *. It avoids unnecessary data copying. Instead of moving data when an element is removed from the front, the red pointer is simply incremented. * Suitable for real-time systems *. Predictable performance due to fixed memory allocation and simple pointer arithmetic. * Simplifies data stream handling * easily manages continuous streams of data, such as audio samples or sensor readings, without dropping samples. 2. Core implementation details. Let's break down the essential components and mechanics. The buffer *, a contiguous block of memory, array, to store the data. This is the core of the circular buffer. Red pointer, head indicates the next element to be read from the buffer. Right pointer, tail indicates the next available location to write data into the buffer. Buffer size *, the maximum number of elements the buffer can hold. This is fixed at initialization. Key operations *. Enqueue, data, or push adds an element to the tail of the buffer. Writes the data at the current right pointer. Increments the right pointer. If the right pointer reaches the end of the buffer, it wraps around to the beginning, index 0. Important if the right pointer catches up with the read pointer, the buffer is full, and the enqueue operation must handle this, example overwrite the oldest data or return an error. Dequeue, or pop removes an element from the head of the buffer. Reads the data from the current read pointer. Increments the read pointer. If the read pointer reaches the end of the buffer, it wraps around to the beginning. Important if the read pointer catches up with the right pointer, the buffer is empty, and the dequeue operation must handle this, example return a default value or an error. Is _empty, Asterisk checks if the buffer is empty, read pointer equals write pointer. Asterisk is underscore full, asterisk checks if the buffer is full. The logic for detecting a full buffer can vary slightly depending on the implementation, see details below. Asterisk size, asterisk returns the number of elements currently in the buffer. Asterisk capacity, asterisk returns the maximum number of elements that the buffer can hold. Handling full/empty conditions asterisk. This is where implementation strategies differ. Two common approaches are: 1. Using a separate count variable asterisk. Asterisk maintain a separate variable, example count, to track the number of elements in the buffer. Asterisk is underscore empty, becomes count equals 0. Asterisk is underscore full, becomes count equals buffer underscore size. Asterisk this method is often simpler to understand and implement. 2. Leaving one element unused asterisk. Asterisk the buffer is considered full when the write pointer is one position behind the read pointer, taking wrapping into account. Asterisk this approach avoids the need for a separate count variable but requires careful handling of the modulo operator. Asterisk is underscore empty, becomes read underscore pointer equals write underscore pointer. Asterisk is underscore full, becomes write underscore pointer plus 1% buffer underscore size equals read underscore pointer. The code examples below will demonstrate both methods. 3. C implementation with count variable. This example uses a count variable to track the number of elements in the buffer. Explanation asterisk. Asterisk circular buffer struct asterisk defines the structure containing the buffer, head, tail, size, and count. Asterisk circular underscore buffer underscore init, asterisk allocates memory for the buffer and initializes the members. It's crucial to check for memory allocation failures. Asterisk circular underscore buffer underscore is underscore empty, and circular underscore buffer underscore is underscore full. Asterisk simple checks using the count variable. Asterisk circular underscore buffer underscore enqueue, asterisk adds data to the tail. The modulo operator handles wrapping around. It checks for a full buffer before enqueuing. Asterisk circular underscore buffer underscore dequeue, asterisk removes data from the head. The operator handles wrapping around. It checks for an empty buffer before dequeuing. Asterisk circular underscore buffer underscore free, asterisk releases the allocated memory. It's important to set cb-buffer equals null to prevent dangling pointers. Asterisk error handling asterisk returns false on failure to enqueue or dequeue, allowing the caller to handle errors gracefully. 4. C++ implementation, object-oriented. This example provides a C++ class-based implementation, offering better encapsulation and safety. Key improvements in the C++ version asterisk. Asterisk templates asterisk uses templates, template type name T, to create a generic circular buffer that can hold any data type. Asterisk classes asterisk encapsulates the data and operations within a class, promoting data hiding and code organization. Asterisk constructors and destructors asterisk handles memory allocation in the constructor and deal location in the destructor, ensuring proper resource management and preventing memory leaks. The copy constructor and assignment operator are essential for proper copying of the buffer. Without them, you'll end up with multiple circular buffer objects pointing to the same underlying memory, leading to crashes when one object is destroyed. Asterisk exceptions asterisk uses exceptions, std overflow underscore error, std underflow underscore error, std bad underscore alloc, std out underscore of underscore range, for error handling, providing a more robust and structured way to signal errors. This is generally preferred over returning error codes in C++. Asterisk const correctness asterisk uses const to indicate methods that do not modify the object's state. Asterisk deep copy asterisk the copy constructor and assignment operator perform a deep copy of the buffer. This creates a completely independent copy of the circular buffer, including the underlying data. Without deep copying, you risk having multiple circular buffer objects pointing to the same memory, which can lead to memory corruption and undefined behavior. Asterisk peek method asterisk allows reading an element at a given index without removing it from the buffer. 5. Considerations for embedded systems. When using circular buffers in embedded systems, consider these points. Asterisk static allocation asterisk prefer static allocation, example declaring the buffer as a global variable or a static member of a class, instead of dynamic allocation, malloc/new. This avoids memory fragmentation and ensures predictable memory usage. If dynamic allocation must be used, consider using a custom memory pool allocator designed for embedded systems to avoid fragmentation. Asterisk buffer size asterisk choose the buffer size carefully based on the application's requirements. A larger buffer consumes more memory, but a smaller buffer may lead to data loss if the producer is faster than the consumer. Asterisk data types asterisk use appropriate data types to minimize memory usage. For example, if you're storing 8-bit sensor data, use uint8_t instead of int. Asterisk interrupts asterisk if the circular buffer is accessed from both an interrupt service routine, ISR, and the main program, you need to protect it with a critical section, disable interrupts, or use a mutex, if your RTOS supports it, to prevent race conditions. Asterisk volatile asterisk declare variables that are accessed by both the main program and an ISR as volatile. This prevents the compiler from optimizing accesses to these variables, ensuring that the latest values are always read. Asterisk memory alignment asterisk be aware of memory alignment requirements for different data types. Incorrect alignment can lead to performance penalties or even hardware faults on some architectures. Asterisk debugging circular buffers can be tricky. Use a debugger to inspect the buffer contents, head and tail pointers. Consider adding logging or diagnostic output to help identify problems. Asterisk consider direct memory access, DMA if the data is coming from a peripheral, consider using DMA to transfer the data directly into the circular buffer without CPU intervention. This can significantly improve performance. Example of static allocation in embedded C**. In this example, the buffer is declared directly within the circular buffer structure, eliminating the need for dynamic allocation. The head and tail pointers are declared volatile because they might be modified by an interrupt routine. Critical sections are used, demonstrated with comments, to prevent race conditions when accessing the buffer from both the main program and an ISR. You would need to provide the disable interrupts, and enable interrupts, functions specific to your target microcontroller. 6. Error handling and thread safety. Error handling in C, return error codes to indicate success or failure, as demonstrated in the C example. In C++, use exceptions, as demonstrated in the C++ example, to signal errors. This is the preferred approach in C++. For embedded systems, you might need to adapt the error handling strategy based on the specific constraints of the platform, example using custom error codes or logging errors to a circular buffer. Thread safety If the circular buffer is accessed from multiple threads, you need to protect it using a mutex, mutual exclusion lock. Asterisk a mutex ensures that only one thread can access the buffer at a time, preventing race conditions and data corruption. Asterisk example, C++ with std mutex. In this example, a std mutex is used to protect all access to the underlying circular buffer. The std_lock_guard class ensures that the mutex is automatically released when the function exits, even if an exception is thrown. Asterisk interrupt safety, without RTOS. If your embedded system doesn't have an RTOS, you'll need to disable interrupts before accessing the circular buffer from the main program and re-enable them afterwards. This creates a critical section and prevents interrupts from interrupting the access. This is shown in the static memory example above. Be extremely careful to minimize the duration of the critical section to avoid missed interrupts. 7. Testing. Thorough testing is crucial to ensure the correct behavior of your circular buffer implementation. Consider these test cases. Asterisk basic enqueue and dequeue. Asterisk enqueue and dequeue a few elements and verify that the correct values are retrieved in the correct order. Asterisk full buffer. Asterisk enqueue elements until the buffer is full and verify that enqueuing more elements fails, or overwrites old data, depending on your implementation. Asterisk empty buffer. Asterisk dequeue elements until the buffer is empty and verify that dequeuing more elements fails. Asterisk wrap around. Asterisk enqueue enough elements to cause the head and tail pointers to wrap around the buffer and verify that the data is still stored correctly. Asterisk multiple enqueue/dequeue operations. Asterisk perform a series of enqueue and dequeue operations in different combinations to test the buffer's behavior under various conditions. Asterisk random data. Asterisk fill the buffer with random data and verify that the correct data is retrieved. Asterisk concurrency. If using threads, create multiple threads that concurrently enqueue and dequeue elements and verify that the data is consistent and that there are no race conditions. Use tools like thread sanitizers to help detect data races. Asterisk boundary conditions. Asterisk test edge cases, such as an empty buffer, a full buffer, and a buffer with only one element. Asterisk error conditions. Asterisk test error handling, such as attempting to enqueue into a full buffer or dequeue from an empty buffer. Verify that the expected errors are returned, or exceptions are thrown. Example of a simple test using assert, c. 8. Optimizations. Asterisk power of 2 buffer size. Asterisk if possible, choose a buffer size that is a power of 2, example 2, 4, 8, 16, 32. This allows you to replace the modulo operator, %, with a bitwise n operation, and, for calculating the wrapped index, which can be significantly faster. For example, index equals, index plus 1, and, buffer underscore size, 1. Asterisk DMA, direct memory access. Use DMA to transfer data directly into the circular buffer from peripherals, example ADC, UART, without CPU intervention. This reduces CPU load and improves performance. Asterisk double buffering. Asterisk use 2 circular buffers to allow the producer and consumer to operate on different buffers simultaneously. While one buffer is being filled, the other is being processed. This can improve throughput. Asterisk data alignment. Asterisk ensure that the data stored in the buffer is properly aligned in memory to avoid performance penalties. You might need to use compiler directives or attributes to enforce alignment. Example of power of 2 optimization, c. 9. Use cases. Circular buffers are used in a wide range of applications, especially in embedded systems. Asterisk audio processing. Asterisk buffering audio samples in a digital audio workstation, DAW, or an embedded audio player. Asterisk sensor data acquisition. Asterisk storing sensor readings, example temperature, pressure, acceleration, in a data logger or control system. Asterisk communication asterisk buffering data received from a serial port, UART, Ethernet, or other communication interfaces. Asterisk real-time operating systems, RTOS implementing message queues or inter-process communication, IPC, mechanisms. Asterisk video streaming asterisk buffering video frames in a video player or camera system. Asterisk data logging asterisk temporarily storing data before writing it to flash memory or another storage medium. Asterisk network buffering asterisk storing network packets before they are processed by a network stack. Asterisk DMA transfer management asterisk using a circular buffer as the destination for a DMA transfer from a peripheral. By understanding the concepts, implementation details, and considerations outlined in this tutorial, you can effectively utilize circular buffers in your C and C++ embedded systems projects to manage data efficiently and improve performance. Remember to choose the implementation that best suits your specific needs and constraints. Good luck.